Vectors as forces. Force is a vector quantity. It has both direction and magnitude. And the unit in SI is the Newton, which is capital N. In imperial units, it was pounds force. They would have pounds force and pounds mass, which was really confusing, but we use newtons. The resultant force is the sum of all the forces in the system, so F1 plus F2 and so on, until we've added all of them together. Here we have an example. We have a boat, and we have forces applied, 1,000 newtons, 30 degrees east of north, and 2,000 newtons directly east. It should be, I guess, F2. Find the resultant force, magnitude, and direction. So we'll start off with a diagram. And I'll just mark north. Force 1 is 1,000 newtons. Force 2 is 2,000 newtons. So I'll make the first one a little shorter. 30 degrees towards the east from north. So call that force 1. Force 2 is 2,000 newtons directly east, so about twice as long. And I'm not doing it to scale, I'm just eyeballing it. There's force 2. And I'll put the 30 right here for now. Find the resultant force. Well, because I've drawn this all starting from the center there, it's easiest to treat them as using parallelogram rule for vector addition, I guess. Meaning our resultant goes diagonally like that. There's our vector. Now, let's see, what do we need to do? We need to add up the forces to get the resultant. Just looking a little closer. Right, this has to be 60, which means this is 60, right? We have the F pattern, making this 120 degrees. So really, I'm going to treat it as a triangle, I guess. And this is 1,000 newtons here. Okay, so the resultant's magnitude, cosine law, will be 1,000 squared plus 2,000 squared minus 2 times 1,000 times 2,000 times the cos of 120. And magnitude of our squared, of course. And that's 7 million. We take the root, get the magnitude of the resultant. And it is 1,000 root 7 newtons, or 2,645.8 newtons. Find the direction of the resultant. So, we will want to have compass directions, but to do this, we're actually going to use one that's in the triangle to start with. So let's see, let's call it alpha right here. Okay, so sine alpha, using sine law, is across from 1,000. And the resultant, 1,000 root 7, sine of 120. And we will get alpha is equal to 19.11 degrees. Now, that's not a compass direction, so I guess the resultant is 2,645.8 newtons, and the direction is north and then to the east, but it's not 19.11, right? Because that's this small angle here. We need the angle from north, so we need the complementary angle of that. So it'll be 80.89 or 81 degrees, I guess we'll say, east of north. Example 1's done. Algebraic resultant vectors, you can add the x components together and the y components, and then you can get direction and magnitude using the components, just like we would when there were other vectors. Find the resultant of the following systems of forces, magnitude and direction. Okay. We'll treat it as components, and we'll work counterclockwise, starting with this one first and then this one, and work our way around. So the x components, and these are components, not vectors. So it'll be 10 newtons to the right, plus 15 cos of 60. The 10 newtons going straight up the y doesn't have a left or right component or an x component. Minus 5. Minus 7.5 cos of 45. Right, because 45 is here as well. And then we have, this is 30, so we have plus 12.5 cos of 30. And get a grand total of 18.022 newtons. The y components. The first one doesn't have a y component. Then we have 15 sine of 60 plus 10. 5 newtons to the left, or negative x direction, doesn't have a y component. Plus 7.5 sine of 45 plus 12.5 times the sine of 30. Oh, my bad. These last two should have been negative because they're going downwards. There we go. And we have 11.4 newtons, 437 newtons. The resultant magnitude is the root of 18.022 squared plus 11.437 squared. That gives us 21.34 newtons. The direction is 18.0 tan of theta. 18, y over x, my bad. 11.437 over 18.022. Theta is 32.4 degrees. So r, as a magnitude, and paired with the direction angle, 20.3 newtons and 32.4 degrees. There's the second example. Equilibrium. A system of forces is the state of equilibrium if the resultant force is zero. So equilibrium occurs when the resultant force is zero. Three forces in equilibrium form a triangle. So in order for three forces to be in equilibrium, they have to add up to the original position or add up to the zero vector. Okay, and you can see the diagram here. These three forces are in equilibrium because they add together and they go back to the starting point of force 1. The forces, in order to form a triangle like this, have to be coplanar. And the largest magnitude, so the largest one, so visually that looks like F3, can't be bigger than F1 plus F2 because then it can't form a triangle. So F3 in this example looks like the biggest. The magnitude of F3, force 3, has to be less than the total of the magnitudes of force 1 and the magnitude of force 2. Find if the system of three forces may be in equilibrium. Well, 12 is much greater than 3 plus 5. So impossible to be in equilibrium. And sometimes people try to draw they have magnitude 3, and then they have magnitude 5, and then they go, oh, magnitude 12, coming back like this, that's 12. Is that really possible to have a triangle do that? No, the 12 is too long, and that's basically what we're saying. So this can't be an equilibrium. Now, if the forces could be an equilibrium, then we'd have to check to see if they're coplanar, but in this case, we don't have to go that far. That's example 3. Example 4. We're going to find the tension in each spring such that the body is in equilibrium. There's no movement. It means the forces have to balance. And there's 2 methods here. The first method is the math method, and then most of you are physics folks, so you're going to love doing the x components and the y components and sorting that out. And I'm going to show you that for a simple system of only 3 forces, the triangle method is often much easier. The other thing to note, and here we're given the force of gravity, but the force of gravity, force is always mass times acceleration, right? The force of gravity, sometimes we're given as F sub g, or just g as a vector, is m times the acceleration due to gravity in g. And for our purposes, 9.8 meters per second squared is sufficiently accurate. Okay. So, I guess I need to add in some paper here and do the 2 methods. I think your notes have space for that. So I'm just going to add in a page. Grid paper's fine. All right. Method 1. And this is really treating the vectors as geometric. Okay. And I like to call it the triangle method. The system, this weight that's suspended, is an equilibrium. There's no movement. So what we have is if you like, the mass coming straight down, okay, the force of gravity, let's say, right, which is 1,000 newtons, 100 newtons. And then we have one of the strings, calling them strings, so, going up this way, up to the left, and we'll call this vector T1, and this is vector T2. Now, I don't know that they want us to find the magnitude of T1 and T2. This triangle doesn't have enough information to solve. We need some angles. So if I just look at this, draw a vertical in here, that support at the top is horizontal. This has to be 40, right? 50 plus 40 plus 90 is 180. So I'll add that in. So this is 40. And then we have, wrong way. This angle to the vertical is 30. So to the horizontal is 30. To the vertical then is 60. So let's see what we can add in on this one here. 60 to the vertical. There we go. Okay, now we have lots of information in this triangle. So find this angle right here. 180 minus 60 minus 40 is 80 degrees. So I'll put an 80 in there. And then to get the forces, we can just use sine law. Tension 1, magnitude of tension 1 over the sine of 60 is equal to 100 over the sine of 80. And the magnitude of the one is 87.9 newtons. To get magnitude of tension 2, that's over the sine of 40, which is equal to 100 over the sine of 80. And you work out the sine law, you get a magnitude here of 65.3 newtons, and the question is done. This is method 1. Works for 3 forces because you can draw a triangle always. 3 forces in equilibrium will always form a triangle. Method 2 is what Mr. Firth maybe taught you. It's the physics way. It's actually a component method. From the mathy standpoint, it is a component method. So method 2, call it the scalar component method. And, I'm not looking for this stuff here. Do you guys remember that from physics, the FBD stuff? That's not me, right? Not for this course anyways. I've done that when I'm doing physics and statics and engineering and that sort of thing, but not for this. But what we're going to do is we're going to put T2 and T1, and we'll put FG, and the only magnitude we know is the 100 newtons here. And other things we should know is that this is 30, right? Because it was 30 here, and this is 50. And I think that's enough. I didn't draw them going up to the flat surface, but it doesn't matter. I just need the directions on them like that. And so the resultant in the x direction, we'll start with that. Oh, it's not a vector. We're just dealing with components, right? Rx is T2 cos of 30 minus T1 cos of 50. And we'll solve this for T2 right away. Of course, that's equal to 0. There's no other forces. They have to be in equilibrium, so the result has to be 0. So we're dealing with the magnitudes, of course, of T2 and T1. So T2's magnitude will be T1, there should be a 1 there, cos of 50 over the cos of 30. Okay, so we solved for T2. And now we're going to do our y, the y components. And so it'll be magnitude of T2 sine of 30 plus magnitude of T1 sine of 50. Those are both pulling up, have to be equal to 100 newtons pulling down. Okay, so I'm going to go ahead and sub in for T2. So what do I mean by that? Well, we have T2 in the equation for the y components. So right here, and we have this value for T2, so I'm going to plug in. So I'm going to have T1 magnitude cos of 50, the cos of 30, times the sine of 30, plus magnitude of T1 sine of 50. Magnitude is equal to 100. Now we can common factor out the T1. And I'll show the step. It's a pain. I want to skip it, but I'll show it so that you can see what I'm talking about. There, I factored out the T1 out of the first term. And from the second term, the sine of 50 is left. That's equal to 100. And then T1 magnitude is 100. And we divide out the remainder there that is left over when we common factor, be cos of 50, sine of 30, cos of 30, plus the sine of 50, plus the sine of 50. And when you plug into the calculator, you should get the 87.94 newtons that we had in the first method. And in the second, to get T2, we plug in to this right here. So 87.94 times the cos of 50 divided by the cos of 30. And the answer should be 65.27 newtons. So there is the two ways of doing it. Now I'm zooming way out. This is the physics method. This is the math method. Which one's easier? Well, if there's only 3 forces, I think generally the triangle is easier. You don't have a system. What we did with the scalar component, I call it the physics method, they're all find methods. The scalar method works when there's more than 3 forces. Triangle works when there's only 3 because they have to be in equilibrium. So this has 3. Triangle works, and it's usually much quicker. Almost always, I think. I don't want to be absolute, but I'm pretty sure it's quicker. Components is really good. If you have 3 forces and it's 3-dimensional, this is a 2-dimensional problem. But if you're in 3 dimensions and there's 3 forces, triangle is still quicker as long as you can find the angles you need. If the vectors are given in component form, then method 2 sometimes becomes really quick. So, depending on how you're given the information, sometimes it makes a difference as well. Okay, so that's example 4. We're almost done the note. Equilibrant force. The equilibrant force is the vector force E, right, capital E, required to be added to a system of forces with resultant force R such that the new system of forces is at equilibrium. So if it's at equilibrium, there has to be an opposing force that keeps it from acting. So if an object is sitting on a table and gravity is pulling down on it, then the table must be pushing up on it, or the floor must be pushing up on it in order for it to be in equilibrium. Otherwise, there would be acceleration. Right? Because equilibrium means that acceleration is 0. Now, of course, rearranging this, that means the equivalent is always the opposite vector from the resultant. So that means they have the same magnitude, just opposite direction. Okay, example 5. Find an equilibrant for the following system of forces. So these forces are not in equilibrium by themselves. Okay, there has to be an equilibrant. So what I'm going to do is I'm going to add up these forces and then find the equilibrant, which will be opposite to the summation of these forces. So we'll start with Rx, and I'll start with the 20 newtons going straight right. So it's 20 plus 20 cos of 150. I could also do the cos of minus the cos of 30, but this way I don't have to. The 50 newtons straight down is not a concern because there's no left-right component to it. It would be 15 times the cos of 270. The cos of 270 is 0. So this works out to 2.68 newtons. The y components, okay, the 20 newtons going to the right has no y component. So we have 20 sine of 150. Again, I could use the sine of 30. That would be fine. And minus the 15. Again, I could use 15 sine of 270. The sine of 270 is negative 1, so I'd end up with negative 15. This is negative 5 newtons. So the resultant, I'll write it in component form. It doesn't say I have to give an angle. It's 2.68 and negative 5. So the x component, or the first component, the horizontal component, is 2.68 to the right. Vertical component, or the y component, is negative 5. Of course, units are newtons, so that's the resultant. The equilibrant has to be the reverse of that. So the force being applied to the system to keep it in equilibrium would have to be negative 2.68 and positive 5 newtons. And that's it.